Hi everyone, it's Mr. Geisman again. Gonna quick review some harmonic motion things and then take us to the next level and look at a few new things. So some things today will be review from yesterday, some things will be new. So to start off, we didn't really give a what a harmonic motion is. So harmonic motion, we talked about it yesterday as a thing, but we didn't give it that definition. Is a motion that will repeat itself. So what goes up must come down and go back up. So harmonic motion is that repetitive motion. A lot of times we refer to that as an oscillation. And an oscillation is a movement in a way that repeats itself regularly. So a oscillation will go up and down, 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 in a circle, in a circle, in a circle, in a circle, multiple times. So when we look at it, we talk about simple harmonic motion, and that's when something oscillates, moves back and forth in a repeated regular pattern, and it's not going in a bunch of different ways. A really good way to think about that is if you had a pendulum, like on a grandfather clock. A pendulum will move back and forth, without changing direction or its motion a whole lot. And when we talk about this, a lot of times we go and talk about cycles. So the oscillation itself is a cycle, and one complete cycle one complete movement, one complete oscillation is what we would call a cycle. When we look at harmonic motion, we're going to be talking about waves. And that oscillation is going to be the traveling from one place to the other, or that a wave is the oscillation that travels from one place to another. On this graph here, we have an oscillation that starts up top, goes down to the bottom, and then back up top. That is one complete cycle. That is one oscillation. We call that a wave. And it carries that energy from one place to another. Right now, you're listening to me, and that is sound waves. Sound waves travel in oscillations, and they fall into harmonic motion. Light and radio also work in that wavelength, excuse me, not in that wavelength, but in that manner. Wavelength is how long it is from one point on a wave to the same point on the next wave. So, how far in distance is it from this top point here to the next top point? So, it's that same point on the next cycle in a wave. We could measure from the bottoms. We could measure from where the line or the wave crosses the equilibrium point. You can pick out any spot along the wave, and the distance from that point to that same point on the next cycle is going to be your wavelength. It's very similar to period, which we'll talk about as well. Frequency is how many complete wavelengths a wave will travel, or wavelengths a wave travels in 1 second. So a frequency of 1, and we measure this in hertz. A frequency of 1 hertz means that we have done one complete cycle, one oscillation in 1 second. And then speed is how fast the wave is actually traveling through a medium. So that energy travels through gases, liquids, and solids. But things like light can also travel through empty space, and how fast it's actually moving, how fast that energy is being uh, moved from one point to another, will determine the wave speed. Right, and yesterday we looked at it, but it's determined by the frequency and the wavelength of a wave. When we look at period and frequency, period is the time required for one complete cycle, and we measure that in seconds. Then, so if we wanted to calculate the period, we would take the amount of seconds and divide it by the cycle. So if it took 2 seconds to do one complete cycle, our period is 2 seconds. Frequency is the amount of cycles per second. So in that same frame, if we measure that in hertz, if we had one cycle in 2 seconds, just like we talked about with period up above, that would give us 0.5 hertz, or 0.5 cycles per second. Period and frequency go together a lot, because when we talk about time that it occurs, we're going to be looking at the period and we're going to be looking at the frequency a lot. So time is going to equal the amount of one cycle divided by the frequency. So how long it's going to take for one cycle to occur is going to be 1 divided by the frequency. So if our frequency is 1 hertz, right, 1 hertz, 1 divided by 1 is going to equal 1 second. Well, if our frequency is 2 hertz, 1 divided by 2, it's going to be 0.5 seconds. So the time it takes for one cycle to occur is going to be 1 divided by the frequency. Frequency then can also be determined by taking the cycle and dividing it by how long it took for one complete cycle to happen, right? We can take frequency is equal to 1 divided by period, and that's how that works. So a pendulum completes one cycle in 30 seconds. It's a really slow pendulum or very, very big amplitude. What are the period and the frequency for the pendulum? Well, we can figure out it took 30 seconds equals 1 divided by frequency. So let's start with frequency to begin with because we don't know. So frequency equals 1 divided by time. 1 divided by 30 seconds is equal to 1 over 30. That is our frequency. 1 divided by 30 is 0.03 hertz, which is a pretty low rate. And then our time, it says it right there in the question. 30 seconds is how long it takes for one complete cycle. Amplitude is the size of the cycle, so how far it goes from that natural resting equilibrium point. So we have a pendulum, the resting point is right at the bottom, and how far it moves from that resting point is the amplitude. We can measure that by an angle, so the angle up top here, so this would be 90 degrees to the attachment point. This might be 70 degrees to the attachment point. That's how we can measure that, or we can measure it in distance, especially if we were looking at a graph. All right, so that's all we have for today. Make sure you attend your meeting, even though it's Wednesday, and we will see you guys tomorrow.